Continuing on with our definitions or vocabulary associated with vectors, we're going to look at scalar multiplication here. Now, vectors can be multiplied by a scalar value or just a numerical value. So I have three different vectors here, vector u, vector v, and vector w. And our magnitude for vector u is 4. So I've just written the number 4 above that vector. The magnitude of vector v is 8, and the magnitude of vector w is 4. So those magnitudes are written in there. Now, if I'm talking about vector v, I know that vector v's magnitude is twice as big as vector u's magnitude, and they both point in the same direction. They're both horizontal vectors here. So I could say that vector v is equivalent to 2 times vector u. They both will have the same direction, it's just the magnitude of vector u I would have to double to get to be equal to the magnitude of vector v. Okay, so as long as they go in the same direction, multiplying by a scalar just means you're changing your magnitude of it. Similarly, I could say that vector u is just half of vector v. So I could take vector v and multiply it by a half, and that would be equivalent to vector u. If I compare vector u and vector w, their magnitudes actually are the same, but do you notice that their directions are opposite to one another? So what I do to make those equivalent is I'm going to say that vector u actually is equivalent to negative vector v. So multiplying a vector by a negative changes its direction to be the opposite direction. So that's an important thing to know. And I could also say that w would be equivalent to, it's the opposite direction to v, and it's half the length of v. So I could say that w is equal to negative 1/2 times vector v. Okay, so a key idea is that when you multiply it by a negative, that is just going to change the direction to the opposite direction. So make sure you make note of that in your note as well. So these numbers in front of our vectors, those are just our scalar quantities there. So the 2, the 1/2, the -1, and the -1/2, those are just scalar values. Okay, so it just is changing the magnitude. And if it's negative, it also changes it to the opposite direction. Okay, now we have talked briefly about bearings earlier on when we were doing some of our trigonometry, but I want to review that because that was something that we needed to maybe spend a little more time on. I noticed that we were struggling, some people were struggling with this. When we're talking about true bearings start at the north. So if I have my compass rose here, north, east, south, and west, goes in that clockwise direction. North usually points up. To do a true bearing or to graph a true bearing, you start at north. So you start at north and you move in the clockwise direction that many degrees. So start at north and go clockwise that many degrees and go clockwise. So if I want to clockwise, okay, so if I want to do a true bearing of 150 degrees, let's say, so for example, if I wanted a true bearing of 150 degrees, it's going to start at north. A full revolution to the south would be 180, so I need to stop before that by 30 degrees. So this is what that vector could look like if it has a bearing of 150 degrees. So it's different than an angle in standard position. Standard position would be like the positive x-axis. This is off of north. So if I wanted another example here, let's say I had the example of 0.75 degrees. That usually, because a full revolution is 360 degrees, usually they put all 3 digits with it. That just means it's only 75 degrees clockwise from north. So that one there would be my 0.75 degrees. And so on. So I could do, maybe I'll do one more if I had an example of, let's say 300 degrees. 300 degrees as a true bearing. That means I'm 270 plus 30 more. I would be heading like something like that. Okay, and better if I actually used a ruler, but this is 300 degrees here. All right, quadrant bearings. What we're talking about are, again, our compass rose, north, east, south, west, but we do it in terms of the north, south, east, and west values. Okay, so the actual north, south, east, west, I'm getting all tongue-tied. So for example, if I had 150 degrees, 150 degrees is really 30 degrees off of south. Okay, so if I think related acute angle, it's not truly a related acute angle, but here's my 150 degrees. If I look at this little 30 degrees in here, I could say that 150 degrees as a true bearing is equal to, or could also be written as, going south, so S for south, but we're veering off 30 degrees towards the east. Okay, so that is another way to represent that, south 30 degrees east. Okay, and often they put that in square brackets, but it doesn't have to go in square brackets, and usually there's no space between like south, the 30 degrees, and the east. It's all kind of put together as one unit. If I wanted to look at my 300 degree, oh wait, before I go any further, some people will also say, but could I also express that as east and then go 60 degrees to the south? Because really that other acute angle in there would be 60 degrees. So you could potentially say east 60 degrees south, but the convention is usually to put south or north first and then your east or west as your second. So this is not going to be seen as common. Okay, usually you put your north-south first and then your east-west as the second part. So not as common there. Okay, so hopefully that makes sense in terms of putting bearings together. All right, moving on. We have an example here. Given the square ABCD, list a vector equivalent to the one that's stated. So I've got vector A to B. Okay, so vector AB, so that says I'm starting at B, A, and heading towards B, and so my vector looks like what I've outlined there. I need another vector that's equal to that. Well, I know that if I were to look down here, D to C has the same direction and the same length. So A to B, vector AB, is equivalent to DC. I could also have turned that around and say that's equivalent to negative CD. So I could go from C to D, go this way, but if I put a negative in front of it, it's going to turn it around and take it back to the direction I want it to go in. Let's take a look at A to E. A to E is this nice little vector here. This is a square, so there are some properties here. The side lengths are all equal to each other. And what happens is when you draw the diagonals in to a square, then those bisect each other, and actually this is equivalent to this, is equivalent to this, is equivalent to that. So those are little properties of squares that you may or may not know. So if I'm looking at AE, that could be equivalent to going from E to C. It's going to have the same length and goes the same direction. Or you could say that's equal to negative CE. Turn it around. A to D goes from here down to here. That would be equivalent to B to C. They go the same direction, have the same magnitude. Okay, and you could put negatives with that too if you wanted to. But I want to look at this last one. A to B plus B to C. So this is starting to get into what we're going to cover actually in our next lesson, but not today. If I look at A to B, we've already have that outlined, and then I'm going to add to it, or go on top of that, B to C. So now I'm down in the bottom right corner. If I'm going from A to B and then B to C, that would be the same thing as going from A and ending up at C. So that would be equivalent to AC. Okay, so there's a kind of a little trick to that, but really when we're adding vectors together, we're going to add them head to tail, because it's like I'm going from here to here and then from there to there. And where do I end up overall? I went from A and it ended up at C. Which kind of brings us to example number 2. Determine the distance and the displacement to get from point A to point B in the diagram. So distance would be like how far did you travel? If you put a pedometer on or you tracked your Fitbit or your GPS and you're tracking how many kilometers or meters or whatever you traveled, that is your distance. So if I look at my pathway to go from A to B that I've outlined here, I'm going from A down to here. That's a total of 1, 2, 3, 4, 5, 6 squares. Over to here is 7. Up 1, 2, 3. That's 10 altogether so far. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. It looks like that's a total of 27 units in distance that we travel if we go from A to B following the pathway that we've outlined there. Now, displacement, on the other hand, is how far you've ended up. You started here, you ended here. What is the difference between the two? So if I look at displacement, here is A, I ended up over here at B. Altogether, that's really only 3 units apart. My ending point's really only 3 units away from my starting point, and the ending point is to the right by 3 units compared to the starting point. So my displacement really actually is only 3 units right. So displacement has direction as well as magnitude. Okay, so my direction is right, my magnitude is 3 units, whereas my distance only had the 27 units because I had all kinds of different distances or directions that I went to get to that final position. So when I'm looking at this, my distance here, that is a scalar quantity versus my displacement, which is a vector quantity. Okay, because it has both magnitude and direction. So hopefully you understand the difference between distance and displacement. If you need to make yourself a little note on each of those, please do that. So distance is the total distance you've traveled to get to your end point versus displacement. It's just comparing your start to your finish and what the difference is if you went directly from one to the other without making all kinds of little turns and stops in between.